Hello everyone, welcome back to the How series. We are beginning the workshop Programming and Optimization for Intel Architecture. Today is session 4. In session 4, we are continuing the module Expressing Parallelism with a session discussing OpenMP. For those who joined us recently, there is a course web page. On this course page, you can download slides that I'm showing. In the slides, all the links are clickable. You can get code of the exercises, watch video recordings of all sessions, and ask questions. You can ask questions in the chat live when I speak during a scheduled time slot, and we will take care of these questions immediately. There is also a forum where you can ask questions offline or ask questions that require an extended answer, where you provide code snippets or go into details of what you're dealing with. Make sure that you are using the Colfax cluster. I will be demonstrating exercises on the cluster, but what truly makes this workshop hands-on is your access to the cluster. You can run our exercises. You can run your own code and experiment with it otherwise for your education. In the cluster, you have access to several Xeon processors and also to Xeon Phi processors and coprocessors for the entire 2 weeks of the workshop. Let's move on to the technical part of the presentation and talk about task parallelism and how it is supported in Intel architecture. Our discussion, as usual, will apply to general purpose Intel processors, such as Intel Xeon, Intel Core, or other multi-core processors, not necessarily Intel. And also it will apply to specialized processors such as Intel Xeon Phi. We discussed them in great detail in sessions 1 and 2. And we are approaching the task of programming these processors with modern code in mind. We want to learn to design a parallel code in such a way that it is highly optimized for current architectures and at the same time portable across the different architectures, for example, Xeon to Xeon Phi, as well as future-proof, meaning ready for the upcoming generations of Intel architecture. Because optimized and portable are often in conflict, there is a set of techniques that make your code, on the one hand, cognizant of the architectural details, but not tied to them. And this is achieved by sticking with standards, such as OpenMP. OpenMP is a standard for multi-threading, vectorization, and offload. We already pronounced the word OpenMP in sessions 2 and 3. Indeed, in 2, we talked about an offload API in OpenMP. Remember, Pragma, OMP, target. And in session 3, we talked about directives for loop vectorization. Remember, Pragma, OMP, SIMD. Today, we are finally getting to the functionality that OpenMP started with, and that functionality is multi-threading. And we will study the construct Pragma OMP parallel and see how it translates to the multi-core architecture and to task parallelism. Using standards-compliant standards-compliant directives or language extensions for parallelism allows you to teach your code multi-core architecture, teach it vectorization, and relying on frameworks such as MPI allows you to use fabrics, and there are also portable ways of using the high bandwidth memory in Xeon Phi processors. What I'm saying is, by complying with certain standards and making your code cognizant of the modern processor features, you are truly designing modern code that is optimized, portable, and future-proof. At this point, I'd like to show you a hardware diagram. It is definitely useful for software developers. We are looking at a two-way Intel Xeon processor. When you're looking at an Intel Xeon processor model name, take a look at this number. This is the wayness. If you see 1, this is a one-way processor. You see 2, this is a two-way processor. There's also four-way processors. Two-way means that on the same system board, you have two CPU chips. In the logical organization of processors in the operating system, they're called packages. Package 0 and package 1. So there is a physical chip representing package 0 and another physical chip representing package 1. Each chip has its own set of cores, and furthermore, every core presents itself to the operating system as two logical processors. This is thanks to the two-way hyper-threading technology. By the way, in Intel Xeon Phi 2nd generation, there is four-way hyper-threading. What you do with this system, if you want to run a parallel program, is you run different streams of instructions on different cores or on different logical processors. With Intel architecture, typically you want either one stream of instructions per core or two, if you want to take advantage of hyperthreading. If your program is not explicitly aware of the multi-core architecture and it doesn't know how to use multi-threading or multiprocessing, then you end up using a single core and not using the rest of the resources on the chip. So definitely this is not a good approach. Before we move on, I want to point out some terminology that is useful in the discussion that follows. So packages represent physical CPU chips, cores are execution units inside of them, and logical processors are representations of a core in the operating system. There is actually some hardware replication between the logical processors, and having more than one logical processor per core allows you to hide memory, to hide the latency of certain instructions and share the resources of the core between multiple instruction streams. Some more terminology. OS proc. This is a numerical ID of a logical processor. So in the operating system, logical processors will be enumerated. The enumeration can be contiguous, like this: 0, 1, 2, 3, and so on, 10, 11, 12, 13, and so on. Sometimes enumeration can be staggered. For example, 0, 1, 2, 6, 7, 8, and so on. 12, 18, depending on how many cores you have. But OS proc is the name for the numerical ID of your logical processor. Sometimes you will also hear words sockets referring to the package. For example, some people would call it a two-way, dual socket processor instead of two-way. And instead of package 0, package 1, you might hear socket 0, socket 1. Of course, this refers to the physical socket on the system board, but the meaning is usually clear. And with the term logical processor, sometimes you will hear logical core or hyperthread, because it is created by the hyperthreading technology, or hardware thread, which is actually a different organization of logical processors from hyperthreads. But usually this jargon refers to the logical processor. And while we're at it, hyperthread is found in Xeon processors and in Xeon Phi of the KNL architecture. And hyperthread switches thread context on demand. not on demand, but as needed. That's a better term. Hardware threads, 4 hardware threads per core, are found in Xeon Phi of the first generation, KNC, and the switching of thread context, meaning which logical processor gets to retire an instruction, is done predictably in round robin. Meaning hardware threads are easier to implement, but they may be less efficient than hyperthreads. What you do with cores and logical processors is you run independent streams of instructions on them. And by running multiple independent streams of instructions, you're implementing MIMD parallelism or task parallelism. MIMD stands for multiple instructions on multiple data. Contrast it with SIMD. When we talked about vector instructions, we said that they implement SIMD parallelism or data parallelism. That SIMD parallelism means single instruction, multiple data, and it is a computer architecture that allows you to execute data parallel algorithms. MIMD is a computer architecture that allows you to execute task parallel algorithms. And the way that threads coexist with vectors is the code of each thread, of each instruction stream, must have vectorization in it. So there will be 2 layers of parallelism. Threads may run different programs on different cores, and inside of the code of each thread, there is code that executes data parallel algorithms in vector units. Threads are actually just one of the ways to occupy multiple cores. Another way to occupy multiple cores is multiprocessing. And I want to explain threads by talking about processes first, because most people will be familiar with processes. Well, definitely, if you're using a modern operating system, you have done multitasking where you are running a web browser in one window and you are running the window manager concurrently with it, and maybe there is a video conversion running in the background and email client fetching mail. This is an example of multiprocessing. Multiple independent processes sharing the resources of your CPU. And each process has its own memory. Well, in fact, it has its own program in the example that I mentioned. Multiprocessing you can also use for computing. If you are solving something like a problem in a spatial domain, think of computational fluid dynamics. You're blowing air onto this toy car and you're computing how it goes around it and trying to optimize air drag. If you're doing that, conceivably, you can split the simulation domain between 2 or several processes and tell this process that it is responsible only for the left-hand side of the simulation domain, and the other process is responsible only for the right-hand side. They are different processes. They are separate instances of the same code, but they work in different simulation domains. Each process has its own memory. So it's impossible for process 1 to access data in the memory of process 2. That's not possible. So when you do multiprocessing, you will often have to do some sort of message passing. There's many ways to pass messages between processes. The most straightforward that anyone can relate to is the file system. One process writes a file, another process reads it. This is possible but not efficient, and there's better ways to do that. For example, in Linux there are sockets, and if you are running these processes on independent machines that do not share memory, then message passing can be done by means of networking. You will need to do message passing in computational applications because in this example, CFD, before you can compute how the wind moves, how the air moves here next to the boundary, you will need to know the air velocity to the left of the boundary. And only process 1 knows that velocity. So occasionally you will need to synchronize data between them. Threads are streams of instructions within a process which share memory. And threads are a different way to occupy multiple threads. You have one process, but it has multiple streams of instructions. One stream is responsible for the left-hand side of the simulation domain, the other for the right-hand side of the simulation domain. And because they share memory, it is actually legal for thread 1 to read or write any data belonging formally to thread 2. And in fact, there is no ownership of data between threads. Memory is shared. Threads just have to be nice enough to only use their memory. And in some cases, threads will try to work on the same memory, for example, on the data next to the boundary. And with threads, you will have to use mutexes to control the concurrency of data processing in these shared data cells. For using threads versus processes, there may be there are various motivations. Mainly, one is dictated by the nature of memory sharing. With processes, you can do multiprocessing on a multi-core machine, right? This goes to one core, this goes to another core, and both of these cores live in the same physical system. It is also possible for process 1 to go to one CPU, and for process 2 to go to another CPU in a different machine, and the only communication between them is networking. Both shared memory and distributed memory architectures are suitable for multiprocessing. Multithreading is different. With multithreading, your only option is to use a shared memory machine. So this is shared memory. A system, for example, a multi-core machine. And this is a distributed memory system. Distributed memory system such as a cluster. So multithreading is also only available with a multi-core machine. But if you're dealing with a shared memory system and you have the choice between processes and threads, here's another consideration that I want to illustrate with this diagram. Suppose you're running a simulation where you don't split the simulation domain between processes, but rather you have a read-only data set that's accessible to all threads or all processes. The particular example I'm showing here, this is a huge particle detector in the Large Hadronic Collider experiment. This detector is called Atlas, and it has a beam of accelerated particles coming from one direction, from the other direction. The particles collide, they produce showers of secondary particles, and there is a computational task to model these showers of particles, how they interact with the metal in these detectors, with matter in these detectors. And the whole geometry of this detector is of order 30 gigabytes. And when you model particle showers, typically you simulate different particles in different processes or in different threads. This is how you split up the work between cores. So each thread will need the entire system, because you don't know where your particle will be. Now it's here, then it produces secondary particles, and now they're there. Because every process would need the entire geometry, you will have to replicate this 30 gigabyte structure in the memory of every process. So if you're using multiprocessing, for example, in a 72-core Xeon Phi, how much memory do you need? 72 times 30 gigabytes, 2 terabytes of memory. That's just not possible. You can install, even with 64 gig modules, you can install up to 0.4 terabytes, and you need 5 times more in your Xeon Phi. So this is simply not feasible. And the only way to parallelize this calculation across all cores is to use multithreading. With multithreading, you can have one copy of your read-only dataset, and all threads will be accessing it. So memory sharing is very powerful with multithreading because you don't have to replicate read-only data across your threads. Okay, hopefully I've convinced you that multithreading is necessary, and in some cases it is the only option to parallelize your applications. Now, how do you get threads into your applications? You need a framework. Threading historically has not been supported by standard scientific computing languages. Well, it was introduced in C++11 with C++11 threads, but prior to that, you could use only similar frameworks such as the POSIX library, the Silk Plus, or the Threading Building Blocks framework, or OpenMP. There's other threading frameworks as well that I don't have time to mention. We will focus on OpenMP because, in my opinion, it hits the sweet spot between low barrier to entry and high degree of tuning. And most importantly, it is designed with computing in mind. So it has built-in support for things like work sharing in loops, parallel reduction, load balancing, and hardware-specific features such as affinity and nested parallelism. While, as an added benefit, recent versions of OpenMP now support vectorization and offload for working heterogeneous systems. Well, let's learn OpenMP. I like to learn by example. So here is the first example for you. This is an OpenMP Hello World program, and it illustrates how OpenMP works. You can write OpenMP programs in C, C++, and Fortran. I'm going to illustrate only C, C++ syntax, and Fortran syntax is very similar. In all languages, execution begins in a single thread, so execution starts off serial. And it goes on serially until you encounter an OpenMP directive, pragma OMP parallel. Pragma OMP parallel begins a parallel region. What happens here is you fork a team of threads. One thread becomes many threads. They each get their own stack, and in parallel they process every line in the scope of this pragma. So all of this will be executed in parallel. At the end of the parallel region, you join the threads, and out comes the single initial thread. So that's the name of the game. Everything inside the scope of pragma OMP parallel is executed concurrently by as many threads as you are running. To compile an application that uses OpenMP, with Intel compilers you have to use the argument Q OpenMP. If you use GCC, the argument is -f OpenMP. To control how many threads you want to use in your parallel regions, you can insert directives in the code, or you can globally control the number of threads with the environment variable OMP numThreads. If you don't set it, then by default, OpenMP will use as many threads as you have logical CPUs. And then you simply run your application. As you can see, I get OMP with 5 threads, and then I get hello world from every thread. Even though I had just one print statement, I get hello world 5 times because the code inside Pragma OMP parallel is executed concurrently by all threads. The idea of threads is to share memory. So this listing shows how to control memory sharing and how it works out of the box. Let's pretend that this is not here. If I have some variables declared before a parallel loop, then when I enter the parallel region, each thread will see the same memory address for variable A and for variable B, meaning they will be shared. This is the default behavior. Sometimes this is what I want. Other times, I may want to have a different memory address for certain variables inside of every thread. This is when I can use the clause private. With the clause private, OpenMP will make a copy of this variable for every thread. So when I say A inside the parallel region, it will mean a different memory address for each thread. If I wish, I can also declare some variables as shared, even though this is the default behavior. I will show you in the hands-on exercises how this is useful, because I can also change the default behavior to none. It is useful when you are parallelizing an existing code, because with no default behavior, the compiler will look for every variable in the parallel region, and if you forgot to declare this variable as private or shared, it will complain. This is important because getting the variable correctly labeled as private or shared is crucial for getting correct results. This approach with clauses will work in all 3 languages of OpenMP. But in C and C++, you have an additional way to control variable sharing, using scoping. If you have a variable declared before a parallel region, then by default it is shared, and all variables declared inside the parallel region are by default private. Always private. Well, that is simply because each thread will produce this variable on its own stack. Okay, so we know how to create threads. We know how to control memory sharing between them. Now, how do we distribute work across thread? There are many work sharing constructs in OpenMP, but probably the most used one is a parallel for loop. Parallel for loops in existing multiple threads allow you to assign different loop iterations to different threads. Each thread will be processing one iteration at a time, so you will end up processing the entire iteration space, but multiple iterations will run concurrently, so you are supposed to experience a speedup. This is an example. I have the green squares represent my iterations, and maybe I can assign these iterations to that thread, those 2 iterations to this thread, and so on. Of course, in order for this to work correctly, my iterations have to be independent of each other, and if they are not independent, we will have to do something special to produce correct results. In code, parallel loops look very simple. You can simply add the keyword parallel to your Pragma OMP, the keyword for to Pragma OMP parallel, and OpenMP library will distribute the iterations of the loop following this directive across threads. So I have Pragma OMP parallel for, immediately after it is a for statement, and then different values of I will go to different threads. No value of I will be processed twice, and never the same value of I will be assigned to different threads. And no more than one thread per iteration. Pragma OMP parallel 4 is actually a combination pragma. It combines Pragma OMP parallel with Pragma OMP 4, and they can be issued independently. In this example, I start a parallel region, so now everything inside the scope of this pragma is executed by every thread. I can use this region of the code, for example, to declare and initialize thread private variables. And then, while I'm still inside the parallel scope, I issue Pragma OMP4, and notice that there is no keyword parallel. At this point, I will team up the existing threads to process this loop in parallel. At the end of the for loop, there is an implicit barrier. So threads are going to wait for each other, and when the entire loop is finished, they will resume execution in the parallel region, because see, this line is still inside of Pragma OMP parallel. And then at some point I will finish the parallel region. So it is really elegant of the creation of parallel loops in OpenMP. And in my opinion, this is a significant advantage of OpenMP over other frameworks for threading, such as pthread, that do not have built-in constructs for loops. Furthermore, in OpenMP, with a very simple modification of your code, you can change the scheduling mode. When OpenMP assigns iterations of your loop to threads, it can use one of the three modes: static, dynamic, or guided. In static mode, OpenMP will decide which iterations go to what thread at the beginning of the loop, and then this decision will not change at runtime. This is cheap. There is very little overhead for scheduling. But it has the disadvantage that if some iterations take longer than others, there may be a case where at the end of the loop, one thread is working and other threads are idling. So you're wasting resources at this point. To prevent that, OpenMP has dynamic scheduling. With dynamic scheduling, different iterations are assigned to different threads one at a time. And then OpenMP scheduler waits for one of the threads to become available. When it is available again, it gets the next iteration to process, and so on. In this way, you do good load balancing, but there is high overhead for scheduling. In an effort to find a sweet spot, there is the guided mode. In guided mode, OpenMP assigns chunks of iterations to different threads. Not one iteration at a time, but a chunk of iterations at a time. And whichever thread becomes available first gets the next chunk of work. The chunk size becomes smaller and smaller as you go on, so that towards the end of the calculation, you can do your load balancing. Which mode works best depends definitely on the nature of the workload, and sometimes you have to try all of them to see. In addition to the modes, you can also tune a numerical parameter called the chunk size. With static mode, the chunk size is how many iterations are assigned to every thread before you loop over. In dynamic mode, the chunk size is the minimal number of iterations that you assign to every thread in every scheduling event. And in guided mode, the chunk size is the minimal size of the chunks towards the end of the calculation. All you have to do to set the scheduling mode in OpenMP is to modify your directive. So if you have pragma OMP4, you can do this: schedule guided, this is a round parenthesis, guided, comma, 16. And this will set guided mode with a chunk size of 16. Plus, in addition to that, you can tune scheduling with an argument such as, I believe it is par schedule. And this is specific to the Intel compiler. This is a compiler argument. Plus, you can set the schedule to runtime and then use an environment variable, OMP schedule. Then at runtime, you can tweak the scheduling mode. I will demonstrate this in the hands-on exercises. So very simple. Just change one keyword and you're changing the algorithm of load balancing. This is, again, significantly easier than load balancing in, for example, pthreads, because with pthreads, the task of going from static to dynamic scheduling is a whole adventure, and you have to write your own scheduler. On the other hand, other frameworks such as Silk Plus have potentially more efficient scheduling modes, such as work stealing. Work stealing is a collective load balancing mode where workers of Silk Plus ask each other for work until all the work is done. Because this is collective scheduling, it is potentially more scalable than dynamic or guided scheduling, which is centralized. At any rate, this is loop scheduling in OpenMP. Okay, so far we have done the easy part. We learned how to create threads. We learned how to control memory sharing. And we learned how to team up threads to do work sharing with for loops. So we learned how to go as parallel as we can. But the difficult part of parallel programming begins when you need to control correctness in your highly parallel program. And this is where you need to invoke thread synchronization. We will talk about it next. The key concept with thread synchronization is a race condition or a data race. This is a condition that occurs when two or more threads access the same memory address, and at least one of these accesses is for writing. Two or more threads try to modify the same data. This is a race condition. Race conditions lead to incorrect and unpredictable program behavior, and you don't want them in computational applications. Here is an example of an application with a race condition. Pretend first that this is not here, and then it's easy to understand what's happening. I'm trying to compute the sum 0 plus 1 plus 2 plus 3 plus and so on plus 999. As a serial application, it is straightforward, and I actually know how to compute it and the sum analytically because I went to middle school, and you probably know that as well. This is the correct answer. Suppose that we wanted to do this calculation in parallel. I'm just going to go and insert pragma OMP parallel 4. This will create threads, distribute different values of I across different threads, and then different values of I will be incrementing the value of total. When I run this parallel code, I will get a result that is incorrect. And furthermore, every time I run this code, I will get a different result. So my program is incorrect and unpredictable. This occurs because of a data race. The variable total is shared between threads, and different threads are trying to increment it at the same time. Sometimes I may be lucky, and one thread goes in, reads the value of the variable, increments it by 1, and writes it back to memory without any interference. Other times, I will not be so lucky. One of the two things may occur. Maybe two threads will read the same value of that variable at once. In this case, I lose some of the increments. Another possibility is that two threads write the value of the incremented variable at once, and then the faster thread will get its result overwritten, and the slower thread will win the race and will have its result recorded. Neither of these situations is good because it produces incorrect results. Generally, to deal with data races, to eliminate data races, you need to use mutexes. And in general, this is true. And I will show you how to correctly use mutexes in such an application. But first, I will introduce mutexes and show you a couple of bad ways to solve this problem. The easiest to use mutex in OpenMP is a critical section. A critical section is something that you put inside a parallel region, and code inside of the critical section is protected from parallel execution. If several threads arrive to the entry of the critical section, OpenMP will allow only one of them to go in, not necessarily in order. This thread will run the entire critical code and then exit. When it exits, another thread goes in, runs the code and exits, and then another thread, and so on. So the critical section will serialize the program. In our case, if we use a critical section, it will produce correct results. But if you look at performance, you will find that this code is unacceptably slow. Not only will it be insufficient, well, not only will, let me say it right, it will actually be slower than serial code. That is because the critical section serializes the calculation inside of it, meaning when one thread tries to do something and another thread is working, the first thread has to wait for thread 2 to finish, and then this thread goes in and does its thing. But on top of that, there is some overhead on threads spinning outside the critical section. So a critical section has its place in parallel programming, but not in this form, not in the form where you serialize every single parallel iteration. There is a more lightweight mutex in OpenMP called the atomic construct. You can see that after, well, again, you use it inside of a parallel region. Again, well, what you see is that unlike a critical section, the atomic construct does not have curly parentheses. That is because it applies to just one line of code, and it protects a single allowed operation on a scalar from concurrent execution. When we do that, correctness will be good, but performance will be bad. It may be, well, this particular code will not be faster than the serial code, but if we had some of the parallel code, maybe we would achieve slight speed up, but not not good. In any case, atomic constructs have their place in parallel programming, but not in this way, not when you serialize every single iteration. By the way, with atomics, this is the list of allowed operations on scalar variables, and don't do any tricks. Don't try to overload these operators to try and cheat. This is just for scalars. It relies on hardware functionality for atomic operations. Okay, so I've introduced mutexes. They allow us to get correct results, but so far we have not used them correctly. And the key to parallel programming is being economical about mutexes, so that most of the time you run in parallel. That means choosing a good parallel algorithm. And there are many parallel patterns out there that you could be using for your applications. I will illustrate one pattern called parallel reduction that will help us to solve this outstanding problem, and you will see that it is used everywhere in parallel computing, so it makes sense to learn everything that OpenMP has to offer with regards to parallel reduction. So here's the correct solution to the problem. Problem OpenMP parallel 4, just add reduction plus total. It says that the variable total, this variable, is shared between threads, but it is special. The only thing that multiple threads will do to it is increment. So something will happen behind the scenes in OpenMP that will make this code produce correct results, and performance will also be good. Indeed, I ran this program, it produced correct results. Well, performance wasn't measured here, and this is a very small problem, but if you increase the problem size, you can definitely tell the performance difference between using mutexes everywhere and using the reduction construct. This reduction construct is very powerful, and it will save you a lot of the time. Good news for people already familiar with OpenMP. In the past, reduction was only supported on scalars. Starting from OpenMP 4.5, you can also do reduction on arrays. Or slices of arrays. So really, this may be the only thing you'll be using in your parallel applications. However, there are cases where the reduction clause will not save you, for example, because it doesn't support the operation that you are applying it to. For instance, finding the top k elements is a reduction operation, but OpenMP doesn't know how to do that. So I'm going to demonstrate an alternative solution of this problem. And it makes sense. It will achieve the same result as here, but it will show you what happens behind the scenes. So this is an alternative solution. It produces the same results and the same performance as the code on the previous slide, but it shows what happens behind the scenes. If I want to parallelize this sum, 0 plus 1 plus 2 plus 3 plus and so on plus 999, I can assign different parts of the sum to different threads. I'm already doing that, right? Thread 0 will add numbers from 0 to 200. Thread 1 will add numbers from 200 through 400 and so on. But the trick that I'm going to do is I'm going to accumulate these sums in thread private variables. Well, in the diagram, I put x0, x1, x2, and potentially I could do that. It is not convenient in real code. So in real code, I will actually use the same variable name, but I will either use the private clause or I will declare this variable inside the parallel region so that each thread has a different memory address for this variable. What I will end up with is several partial sums. Each thread has its own partial sum at the end. And I have to add together these partial sums into the shared variable. In other words, I have to reduce all the partial sums into the shared global sum. And reduction in this case means aggregation. It doesn't mean making something smaller, it means aggregating something. This operation is actually a data race, so I'm going to partially serialize it with atomics. And in this case, murexes are used economically, so they are justified. I'm going to use as many synchronization constructs as I have threads, which is, well, in this case, 5. This is much less than the 1,000 that we were initially trying to use. In code, it will look like this. I start the parallel loop. Inside the parallel loop, I create a thread private variable to store the partial sum. Then, with pragma OMP4, I team up all threads to process this iteration space in parallel, and every thread will be incrementing its own private counter. At the end of the parallel loop, there is a barrier, so threads wait for each other, and then they continue, and they resume execution still inside the parallel region. So every thread is going to run this line of code. And because threads will do it at the same time, I have to protect total from concurrent execution, and I do it by putting pragma OMP atomic before this construct. I could use pragma OMP critical, which would still be justified if n is large enough. So this is the reduction pattern for you. It will save you a lot of the time when the built-in support for reduction doesn't work. It's useful to understand this principle because you can also use it in other frameworks and in distributed memory programming. I've demonstrated the key concepts and tools of OpenMP: how to create threads, how to control variable sharing, how to team threads up to do work sharing, how to use murexes to control data races, and how to use reduction for the most common, possibly the most common pattern in parallel computing. I want to connect what we talked about today to yesterday's topic and discuss the coexistence of threads and vectors. I mentioned that in OpenMP, I mentioned that in Intel processors, you have the CPU, and inside the CPU, you have cores possibly presenting themselves as multiple logical processors. And you put threads on the different cores. And then the code of each thread has to have vector instructions in it to take advantage of the vector processing units inside of cores. So naturally, Intel architecture likes parallel algorithms with 2 layers of parallelism. The outer loop must be suitable for multithreading, meaning it should have task parallelism. The inner loop must be suitable for vectorization, so it should have data parallelism. And this is actually quite flexible. This is different from the requirement that you need, for example, for a GPU, where basically you need a single massively data parallel loop. However, if you just have a single data parallel loop, you can still use Intel architecture because definitely, if you can run multiple instructions on multiple cores, you can run the same stream of instructions on multiple cores. So if your application is centered around one loop, trying to do something like this might still work. Pragma OMP parallel for SIMD. It will try to glue together several contiguous iterations in I for vectorization. And then chunks of these vector iterations will be distributed across threads. This might work in some cases. In other cases, the compiler might need a little help. And this help may come in the form of strip mining, a programming technique where you rewrite a single loop as two nested loops. Strip mining allows you to expose opportunities for vectorization and multithreading, because, well, the hardware and the compilers try to look for these two layers of parallelism. This is an example of a strip-mined loop. There's a lot of code, but conceptually it's simple. I have an outer loop going from 0 to n with a certain stride, that is a tuning parameter of my application. And inside of that loop, I have little I going from II to the next value of II with a stride of 1. So I do the same work in the same order. I just write it as two loops so that I can vectorize inner and parallelize outer. Vectorize inner, parallelize outer is an acronym that one of the students of the house series taught me, and this is a mnemonic rule for the mnemonic rule is VIPO, vectorize inner, parallelize outer, mnemonic rule for writing parallel code suitable for Intel and Intel-like architecture. The reason that this code is complicated, see I have this n trunc and remainder loop, is that I wrote it in such a way that n does not have to be a multiple of the strip size. If it's not a multiple, it will still work because the remainder loop will take care of the few iterations at the end. We talked about OpenMP and studied the key concepts and constructs in OpenMP. And you can definitely learn more. And you can actually learn more from the OpenMP specification. The OpenMP specification is a long and extensive document, PDF document that you can download, explaining how OpenMP constructs should work. Some implementations have certain variations or added features, but overall, this is the rule for OpenMP. I also found a very convenient, it's a little outdated, but still very good functionally tutorial from the Lawrence Livermore National Lab. And all these links are clickable. You can click them to learn some new features of OpenMP and also reiterate what we talked about today. So PragmaOMP parallel creates threads. PragmaOMP 4 processes a loop with threads. There's also PragmaOMP task for asynchronous tasks, and for example, you can implement parallel recursion using tasks. There are mutexes, critical and atomic. There's barriers and synchronization points. We didn't talk about it because it doesn't belong with simple parallel algorithms. There's also ways to give different threads completely different code with OMP sections or OMP single. For complex parallel patterns, you might find useful PragmaOMP flush. It enforces memory consistency across this barrier. And sometimes it is useful to employ ordered parallel loops in OpenMP, which gives you partial loop serialization. In addition to these directives, you can read about the environment variables that OpenMP supports. They all begin with OMP. And you can also read about the support functions of OpenMP. I will demonstrate some of them in the hands-on exercise part, and you can read more here. And I have also a couple of additional links with reading that you can do. There's a paper on Colfax research illustrating a parallel reduction in the same physics experiment. Remember, particle tracks in cylindrical particle detectors. And there's resources again. You can click and go there. This is the link to specifications, the big PDF document. This is a video course from Intel that you can use for additional information on OpenMP. This is a written tutorial from the Lawrence Livermore National Lab, and our book, this book, also talks about practical usage of OpenMP. We do have a hands-on demonstration scheduled for the second hour, and we will resume in 5 minutes. Okay, I have 2 demonstrations planned for OpenMP, and I've logged into my cluster. You can log in as well, or you can just follow along with the demonstration. For For this exercise, we will go to House Series Labs, Chapter 3, 302, OpenMP Basics. And here I have hello.cc. This is my code. What's happening? And as you can see, it has some placeholders. There are so many available threads, hello world from thread session such. We are going to parallelize this code and experiment with variable sharing. I will have two windows open. That's the plan. Okay, that worked. Go to House Series Labs 302. Right. So I'm going to compile and run this application just locally. I think I've introduced some garbage during editing. Make again. Okay, finally compiled the original code. As you can see, I'm also producing an executable for the CPU architecture, for Knight's Corner architecture, and for Knight's Landing. This is all good, and it illustrates that the code that we're going to make is going to be portable across these platforms. But I'm only going to use the CPU executable, app CPU. When I run it, nothing exciting happens. There are -1 available threads. Hello world from thread -1. The idea, of course, is that this is just a placeholder. If you want to query how many threads OpenMP has at its disposal, I can use the function OMP get max threads. By the way, there is a function called OMP get num threads. It is not applicable. It only works inside the parallel region. Because we don't have any parallel regions, I'm using OMP get max threads. So make again. There is a compilation error. OMP get max threads is undefined. That is because this function is a part of the OpenMP library. And to get access to its signature, I have to include omp.h, the header file. Now I can recompile. Compilation succeeds. And I will run it locally on the login node to see that I have 8 available threads. Why 8? Well, that's because this virtual CPU has 8 threads. I can also queue it for execution on the cluster on a regular CPU, on a Knight's Corner coprocessor, and on a Knight's Landing processor. As you can see, there are built-in targets in the makefile. Looks like jobs have finished. And there, I will be able to see how many threads OpenMP chooses to use on those platforms. So on the remote CPU, OpenMP chose to use 48 available threads because it has 2 packages. Each package has 12 cores. And each core has 2-way hyperthreading, so it represents itself as 2 logical processors. The product of that is 48. How about Knight's Corner? On Knight's Corner, OpenMP chose to use 244 available threads. That is 61 cores times 4 hardware threads per core. And on Knight's Landing, OpenMP will be using 256 threads. This is 64 cores times 4-way hyperthreading. Okay, so by default, OpenMP uses as many threads as I have logical processors. If I want to change it, I can set OMP num threads to something else. I can use fewer threads than I have logical CPUs. Sometimes it is justified, for example, to maximize bandwidth. I can potentially use more threads than I have logical processors, but that is rarely justified. So I will stick with, well, for example, 4 threads. Okay, now let's take care of this next placeholder, hello world from thread -1. Of course, the idea was that it will be a hello world from an actual thread, and that's easy to fix. But the idea here is that we want to parallelize this part. So I will put pragma OMP parallel, and this is where parallel execution starts. Each thread will run the same exact code. When I run it, I get hello world 4 times. Of course, you rarely want every thread to run the same code. You want different threads to run different codes or work on different parts of a simulation domain. And you can differentiate work between threads by querying the thread number. Each thread identifies itself with a number. They are 0-based. I believe in Fortran they are also 0-based. Yep, that's hello world. As you can see, the output is not in order, and every time I run, the output may be in a different order. Well, this is how we can create threads and differentiate work between them. How do we take advantage of memory sharing? If I have some variables declared here, these variables by default are shared between threads. So in thread such and such, A is equal to that, and address of A is equal to this. I will print A and the address of A. Rebuild, rerun. As you can see, in every thread, A has the same value, and the memory address of A has the same exact value. If I make A private, what's going to happen? As you can see now, A has garbage for value, and the memory address of A is different in different threads. The reason why A is garbage is that the clause private does not initialize A to anything. So if I wanted to make a private copy and initialize it to the value in the initial thread, I could use the clause first private. The result will be similar. Different memory addresses for A, but the same value. Let's make it shared once again and see how memory sharing works. What I will do is I will change the value of A after printing it. I will set A to 1000 plus thread ID. Recompile, rerun. So what happens now, A has the same memory address everywhere, and some threads managed to grab the old value. For example, here thread 0 grabbed the old value, then it changed A to 1000, and thread 2 saw the value 1000. The output does not necessarily correspond to the actual order in which threads worked. So thread 3 printed the value set by thread 2, but thread 1 still saw the initial value. So this is how memory sharing works. Of course, this is not going to happen if A is private. Consistently, you will see A is equal to 7 because any modifications made to A by one thread are not propagated to any other thread. Each thread has its own memory address. Okay, so that is convenient. How about some work sharing constructs? Oh, I promised to also illustrate this functionality. If I have a region that I'm trying to parallelize, and I'm not sure how many variables are inside and what to do with them, I can set temporarily the default sharing to none. And then if I forget to specify any values as private or shared, the compiler will complain A must be specified in a variable list. So, for example, shared A or private A. Both of these are going to work well. Okay, now let's move on to parallel for loops. So if I have a loop, and in this loop, for example, I simply print the value of I, how will it work? If this is what I do, what I end up is a loop that gets executed as many times as I have threads. As you can see, well, I can sort the output to see it more easily. Each value of I was processed by every thread. This may be what I want, but if I want to do work sharing, then I have to distribute this loop across threads. And I can do this by putting pragma OMP 4 before the loop. Recompile, rerun. As you can see, thread 0 got the first 3 values, thread 1 got the next 3 values, thread 2 got the next 2, and so on. So OpenMP by default tries to split up the iteration space into approximately equal contiguous chunks of threads. This is the default behavior. I could change it if I wanted. For example, I can set schedule to dynamic. And if I do that, then the assignment of iterations to threads will be decided at runtime. Here, for example, thread 0 was so fast that it processed all of the iterations. There, thread 0 was slower and thread 2 was fast, so it got most of the iterations, and thread 3 did nothing. Every time I run, the assignment will be different. I can also set schedule to runtime. The effect of that is that my program will become sensitive to an environment variable. So this is static assignment. My program is now sensitive to OMP schedule. If I set the schedule to dynamic, then without recompilation, I can rerun and I will see dynamic scheduling. If I reset this variable to static or unset it, I get static scheduling. I can also experiment with the chunk size. For example, static comma 1 will assign one iteration to every thread, and then they will go in round robin. See, 0, 1, 2, 3, 0, 1, 2, 3. So there's parallel loops for you. I think this is a good exercise so far. And to really experiment with muxes and with parallel reduction, I'd like to do another exercise. This one has something to do with computational applications. So we will do useful work. Let's go to lab 303. And here, open integral.cc. What's happening in this lab is numerical integration. I'm trying to compute the value of the integral. From x, let's do it like this, from a to b, some function f of x with respect to x. Approximately, I'm computing it as the sum of f of x I plus 1/2 times delta x. And here, delta x is the integration interval, which is the integration interval divided by n, and x I plus 1/2 is a plus delta x times I plus 1/2. So I'm approximating the area under the curve with a series of rectangles. So this is delta x. I'm finding the middles of the intervals, building rectangles like this, and approximating the area under this curve, which is plotted by f of x, as the sum of the areas of these rectangles. 1, 2, 3. Most people here are probably familiar with this procedure. The code is currently serial, and my task is to parallelize it. As I work on the parallelization, I'm also going to create a log just to track our performance. And I will measure performance on the CPU, on KNC, and on KNL. So let's first establish a baseline, compile, so I'm submitting it for execution on the queue. It will take a few seconds, but let's see what's inside. I have a loop that performs several timing trials. In each trial, I change the upper and lower bound of integration. I make a lot of integration steps, 1 billion. This is my running sum for the integral. And here I use a very convenient timer, which is actually also a part of OpenMP. OpenMP get W time. It returns the current time as Linux epoch with microsecond resolution. It is quick, simple to use, and I like using it for timing my applications. So this is start timing. This is the integration loop. And here's end timing. Inside the integration loop, what I do is I compute x, and then I increment the integral by 1 over the square root of x delta x. So here's my performance result. As you can see, the code prints out, let's try again. The code prints out the result and the analytical value of this integral, so the error is small. If the error is small, I get correct results. This is how long it took, 5.2 seconds. On an Ivy Bridge processor. On night's corner, 7.1 seconds. Lower is better, so night's corner is doing worse. And night's landing is doing better, 1.4 seconds. The key to improving the performance of this code is parallelism. Definitely this loop has data parallelism and task parallelism. Data parallelism because, well, different values of I can be executed in multiple vector lanes. And if actually you take a look in the optimization report, you will see that this loop was vectorized. So the loop is in line 19. It was vectorized, so good job, good job compiler. But this loop doesn't know yet how to use multiple threads. And this is where we come in and put bravely pragma OMP parallel. Right? I parallelized my calculation. Oh, wait a second. If I just put pragma OMP parallel, then every thread is going to run the entire loop. This is not what we want. What we want is work sharing. We want different iterations to go to different threads. So I put pragma OMP parallel 4. So submitting to the queue again. And let's see what comes out. Okay. On the CPU, the time is 0.22 seconds. And I'm tempted to look at the KNC and KNL results, but I noticed something else. The error is huge. That's because our result is way smaller than it should be. Definitely we went through a similar example in the lecture part of today's presentation, so we know what's happening. The value integral, the variable integral, is shared between all threads. And all threads are going to concurrently try to increment the integral. When they do that, what we end up is a data race. Thankfully, we know what to do with this particular data race, because all that the threads are doing to this variable is incrementing it. And this is a reduction pattern, and OpenMP has built-in support for reduction, so we just need to put reduction for the operator plus on the variable integral. Submitting to the queue again. Okay. All right, so now the result is close to what it should be. The error is small everywhere, and the time is indeed 0.22 seconds. This is on the CPU. On Knight's Corner, .0.42 seconds. 0.042 seconds. And on KNL, 0.016. So this is a good solution. Let's analyze it for a minute. First, what is the speed up? .2 divided by 0.22 is 23.6. Well, maybe 3 significant figures is too much. How about 2 significant figures? Then 7.1 divided by 0.042 is 169. 2 significant figures. And 1.4 divided by 0.016 is 90x, well, 88x. Is it a good speedup? So, on the CPU, generally you expect one thread to fully utilize a single core. This is how CPUs are built and balanced. So the number of cores is your expected speedup if you have a computational bound application. The CPU had 24 physical cores and the speedup is 24. So we are good. On Knight's Corner we have 61 cores. So why is the speedup greater than 61? That is because on Knight's Corner, with the hardware thread organization, one hardware thread fires only every other cycle. So with one thread running on the entire chip, you're using half a core. So here you use one core, here you use half a core. Well, half the cycles of a core. So the minimal speedup that you expect for computationally bound applications is 2 times the number of cores, so 120. We actually see a little more than 120. I think that is because we are able to mask some of the latency of long latency operations, maybe the square root or the type conversion. We are able to mask these latencies by using 4 threads per core. And a similar story on Knight's Landing. In principle, you're using one core with one thread, like on the CPU, but generally it is not able to mask the latency of long latency operations. So even though Knight's Landing has 64 cores, still you expect a speedup slightly greater than 64 because with 4 threads per core, you expect to mask some of the low latency operations and get a better speedup. So our speedup is good. Something else I want to look at is the timing. We made several trials, and in these several trials on KNC and on KNL, the first trial took abnormally long. That is because of thread initialization. The first time we spawned a parallel region, some time should have passed to initialize threads. And then when we revisited this parallel region, remember we have multiple trials. How does it work? We have multiple trials here. So this parallel loop starts and stops many, many times. And if you do timing, especially with small kernels, you have to be aware of that. If you do timing and it takes a while on Xeon Phi, doesn't mean that it's working poorly. It just means that you're not really measuring sustained bandwidth. You can either do what I did, make multiple trials and ignore the first one, or you can warm up the threads like this. And then you should get rid of the warm-up effect. Let's see. Well, there is still a little bit of a warm-up effect, but much less than in the previous case. So OpenMP is smart about spawning threads. Once it has threads working, it will keep them active, in the case of OpenMP, for 200 milliseconds. And if you revisit a parallel region within 200 milliseconds, you will have most of the machinery still active. You can change this period, if you want, using a variable KMP block time, and you can look it up if you wish. Well, we obtained a good parallel program with very little effort. All we did is inserted one directive, pragma OMP parallel reduction plus integral, and it gave us thread parallelism. Interestingly, it actually also preserved data parallelism. If you look in the optimization report for line 24, you will see that the OpenMP defined loop was parallelized. That's good. But also, this loop was vectorized. So the compiler knew that it has to glue together several iterations in I and convert everything that we're doing here into vector iterations, as we discussed in session 3. And then it also knew that it has to distribute those vector iterations across threads, like we discussed today in session 4, and it knew that integral is a special variable. All we're doing with it is we are incrementing it, so it implemented the reduction pattern behind the scenes. Even though this is a good solution, I want to demonstrate an alternative solution because it will be necessary in the future. Suppose that you have an operator for which reduction is not defined, or a data type for which reduction is not defined. How will you get out of this pickle? Integral is a shared variable. My first idea would be to separate the parallelizable calculation as much as possible from the data race, and then use a mutex to control this data race. For example, like this, pragma OMP atomic. I could try to run it, and in fact, one time I did, and it took a while. So I'm going to cheat. And just for this test, I will reduce the number of steps by 1000. So 1, 2, 3. So I will multiply the time that I actually get by 1000, and it will give me a good estimate of what it would have taken with the original number of steps. So we obtained a good result, but I'm trying to demonstrate an alternative solution. The first idea is to use a mutex, and let's see what performance it gives us. On the CPU, 123 milliseconds, but I have to multiply it by 1000. So it would have taken 123 seconds if I only used the original number of steps. Knight's Corner, 570 seconds, and Knight's Landing, 3000. Definitely not acceptable, much slower than the initial code. So just inserting the atomic construct is not a good idea. We have to be economical about it. And to be economical about it, what I will do is I will implement a reduction pattern, just like I illustrated in the slides, and I have a recipe for it. It involves 4 steps. We will see this pattern many, many times in this course, so I think it makes sense to illustrate it now. I will, as the first step, I will separate pragma OMP parallel from pragma OMP 4 and insert curly parentheses here. This will give me an opportunity to insert some code before and after this pragma. So here I can insert an initialization of a thread private variable, integral th0. This is step 2. And step 3 is, instead of using the integral, I will use integral th. At the end, I will end up with a bunch of thread private results. So while I'm still inside of the parallel region, but not inside of the parallel loop, I will do the reduction. Because this is a data race, I insert pragma OMP atomic here. We will see this pattern many times again, so don't worry if you don't quite catch it this time. But what you will see is that it will produce the same timing as this optimal solution with reduction. Let's call it reduction by hand. .22 seconds. And I think it will be similar results on Knight's Corner. Yes, 0.042 seconds. And on Knight's Landing. So that's good. If the parallel reduction clause does not work for you, you can implement reduction by hand using that pattern that I mentioned. Split pragma OMP parallel from pragma OMP4, insert initialization of thread private variables, use thread private variables where the data race was, and at the end, do a reduction using a lightweight murex. Well, this was my quick demo of OpenMP. I think we really studied tools that will help you in a huge variety of algorithms. You need to remember from today's presentation that cores are there to run independent programs, and you can utilize cores with multiple processes or multiple threads. Threads are convenient because they share memory with each other, so you save the memory overhead compared to processes. You need a threading framework to run threads, and we studied OpenMP, which is from the top designed for computing. With OpenMP, it's easy to go parallel, but you need to worry about data races. And it's not just with OpenMP, with any parallel program. You can use murexes to control data races, but you need to be economical about them and use a good parallel algorithm. Threads must coexist with vectorization, and that should be in each thread. And Intel compilers often know how to do that. Sometimes you need to give the compiler a little bit of help with the help of with the technique called strip mining. We will revisit this in session 7. In the next session, we will study the third layer of parallelism, multiprocessing in a distributed memory system with MPI. So we have learned how to use all cores with all of the vector processing power. And next time we will learn how to use multiple computers connected together into a common network in a cluster. Thanks for joining us today. I am wishing everybody a good day, good rest of the day. And I will talk to you again in session 5 tomorrow. Goodbye.